Magnetic fields. In this video, we'll be covering magnetic fields, the diagrammatic representation of them, and the magnetic field strength. Humans have known about magnetism for a long time. It was discovered that lodestones always pointed in the same direction, and this was towards the North Pole of Earth. People use this information to assist with navigation, such as on ships. Now, it was only 2 centuries ago where it was discovered magnetism was related to electricity. Electric currents are just moving charged particles, and when charged particles move, they generate magnetic fields. So all electric currents, moving charged particles, have magnetic fields that are associated with them. Now, this magnetic field that's created when a charged particle is moving is separate to the electric charge on the particle, but exists at the same time. When a charged particle is not moving, being stationary, there is no magnetic field that is associated with it. A magnetic field is a vector representation of the influence around the magnet and is defined in terms of magnitude and direction. So for a bar magnet, as in this diagram here, it's easy to see that the direction of the magnetic field goes from north to south. But if we consider a magnetic field associated with moving charged particles, we cannot see this north or south. So how do we determine it? We'll get to that a little bit later. The magnetic field lines in a diagrammatic representation are lines of force, meaning the direction of the arrows or the field lines is the direction of the force. So comparing this to gravity, the direction of the field at any point is the same as the direction of the force on the mass placed in that field. Now, in an electric field, the direction of the field is the direction of a positive test charge placed in that field. And in a magnetic field, the direction of the field is the direction of a force on the north pole of a magnet placed in that field. So let's consider a dipole as a small bar magnet or a compass needle. To investigate the direction of the field, we place this compass needle in that field, and the needle aligns itself with the field lines, with north following the direction of the field lines. Now, in our considerations, we consider the north of the dipole. However, you cannot get a north by itself. There's always a south associated with it. So if we had a bar magnet with a north and south end and we cut it in half, the new pieces will have a north and a south. And this is because magnetic fields form closed loops. Now, the magnitude of a magnetic field is represented by the number of field lines that cross a certain area. For a weak magnetic field, we have few lines, and for a strong magnetic field, there are many lines for that area. This is an example of the magnetic field associated with a bar magnet. You can see that unlike electric fields, where the field lines leave and return the material at right angles, magnetic fields don't do this. And you can also notice in this diagram that magnetic fields always form closed loops. So even this line here will form the loop all the way around and come back here, even though looking closely, it's a straight line. This is another example of the influence of magnetic fields in close proximity to each other, similar to when we looked at electric fields. You can see at any point, if we placed a north dipole in that location, it will point in the direction of the arrows. So here, it will point away from north and towards south. So with this information, it's interesting to look at Earth's magnetic field. And we can see from this diagram on the left here, the field lines point towards our geographic North Pole and away from our geographic South Pole. So when we're holding a compass on Earth, it points towards the North Pole, which means that north needle is attracted to magnetic south. So what that means is our geographic north and our magnetic north are 2 different things. What we can also see is that the magnetic north and the geographic north don't perfectly line up, and the magnetic field of Earth is slightly shifted from the geographic definitions that we have given. So when we talk about navigation, true north is the north that is our geographic north, not our magnetic north. So we've briefly discussed the magnetic field around a bar magnet situation when there is a north and a south. However, we can also consider a current that produces a magnetic field. So we've got a wire that represents the path of motion of the moving charged particles. And in these 2 situations, the wire is moving in and out of the screen. In this situation on the left, the X represents the wire moving away from us, or the current in the wire moving away from us. And the dot in the center of the wire represents the current coming towards us or out of the page. Now we can remember this by considering an arrow, and when we shoot the arrow away from us, the feathers on the back of the arrow can represent this X in that it's moving away from us. However, if the arrow is moving towards us, we see the sharp point. It's also important to note in these diagrams that very close to the wire, the field lines are close together, indicating a strong magnetic field. However, further from the wire, in this region, the field lines are further apart, meaning it's a weaker field. Notice in both these cases, where the current is traveling in the opposite directions, the magnetic field, represented by these arrows, travels in the opposite direction as well. So we can determine the direction of a magnetic field around a straight current carrying conductor by using the right-hand curl rule. So we do this by grasping the wire with our right hand. Our thumb is in the direction of the current, and the direction of your curled fingers is the direction of the magnetic field. We can also have a magnetic field when the current travels in a loop. In order to determine the direction of the magnetic field around a loop, we again grasp the loop in our right hand, our thumb points in the direction of the current, and our fingers point in the direction of the field lines. And you can see this diagram on the right here. If we grab the loop with our right hand, our fingers will actually be within the loop, and the direction of our fingers will point in the direction of the magnetic field lines. Also important to note here that within this loop, the magnetic field lines are uniformly spaced, meaning it's a uniform magnetic field. Another situation we'll look at is that of a solenoid. So a solenoid is just a continuous wire wrapped around a core, and effectively it's a series of loops stacked together. To find the magnetic field around a solenoid, we again use our right hand. This time our fingers point in the direction of the current, wrapping around the solenoid, and our thumb points in the direction of north. So we can see in this diagram on the right, if we wrap our fingers around this solenoid in the direction of the current, our thumb will be pointing left, which is the direction of north. Now, because solenoids have so many coils that are stacked together, they can be very powerful in producing magnetic fields. Now, the magnetic field around a solenoid only exists while that current is moving, and if the current is turned off, the magnetic field will stop. The magnitude of the magnetic field around a current carrying conductor can be determined by this equation here. In this equation, R is the distance to the conductor. This term is a constant for the magnetic field around the conductor, and the value is 2 times 10 to the negative 7 meters per amp. I is the current in amps. B is the magnetic field strength, and it has units of Tesla, and it is also a vector quantity. In the three scenarios here, use your right hand rules that we've learned to identify the correct magnetic field.